Alright, so now let's take a look at part B. We can immediately tell this is a quadratic equation, and it's going to have one of those U-shapes when we graph them. So I can guess that this is not going to be a bijection, but I think the quick example is if we plug in one of the numbers. So let's say if we plug in 1 for x, we're going to get the same value when x is negative 1. So therefore, this is not a bijection. And I think so for these problems, by providing just one counterexample is sufficient. For the rest of these, I think I'm going to do, for all of these, I'm going to write up the detailed solutions so you guys can see the process of proving something is one-to-one and onto. So I'll post that along with the rest of the videos. Alright, now let's go on to section 2.5, Cardinality of sets, and do some similar problems to the practice problems, or the homework problems. So number 2, I would like to go over problem number 2, because I think these are similar to the assigned problem of 1. Okay, so we're trying to tell if this is either countably infinite, or if we can we need to exhibit one-to-one correspondence between a positive set of integers and the set. All right, so let's take a count. Part A, integers greater than 10. So this is going to be a countably infinite, and to be more specific, we can do well, this is countably infinite because we can count. Will be starting from 11, 12, 13, 14, and it's going to go infinitely. So to show the one-to-one correspondence, we can do the mapping. We can start at 1, and this would go to 11, and 2 would go to 12, 3 would go to 13, and so on. So this would have the relationship of n being mapped to n plus 10. So therefore, this does have the one-to-one correspondence between a set of positive integers and the set itself. And this is countably infinite. Alright, let's take a look at part B, the odd negative integers. So the odd negative integers, this will be negative, the set will be -1, -3, -5, and so on. So as you guys can guess, this is pretty similar to the first one, which is this is going to be countably infinite as well. And let's show the mapping. So the first element maps to -1, the second element maps to -3, and so on. And we can guess that the nth element, this kind of has the role of -2n minus 1. Alright, and so by just showing this portion, we have shown the one-to-one correspondence between the set of integers and the set, or positive integers. Alright, so that was for B. Let's talk about C. So part C is the integers with epsilon value less than 1 million. So this would be the set of would be 9, and the next number would be -9, 9, 8, and it's going to continue all the way to 0, +1, actually, and it's going to continue to grow until it reaches 9. Okay. Alright, so as we can see, this is a finite set. So the answer for C is finite. And if we wanted to talk about the cardinality would be, I guess, one. This would contain 1 million numbers, and this would contain just one less than a million. So cardinality of part C would be just one less than 2 million. But we're talking about cardinality just because this is a finite set. All right, so let's talk about D, the real numbers between 0 and 2. So this is uncountable, and you can prove this using the diagonalization, which is illustrated in the book. I can also post additional resources under the additional resources folder. I can post a video that proves how numbers are uncountable for real number sets, and it uses the diagonalization. All right, so E, the set A by Z, this is the finite, this would be the positive integers, where A is 2 and 3. So this is also, actually this is just countable, because we can count, this would be the set of 2, 1, and we can actually list all of them out. There's 3, 1, 2, 2, and 3, 2. What else? 2, 3, 3, 3, and so on. So this again would be countable, and this would be 1 to 1. F, last one, the integers that are multiples of 10. So this is also another countable set. We can list them out. Just to show the 1-to-1 correspondence, we can do the first maps to 0, the second number maps to 10, the third number maps to -10, the fourth number maps to 20, the fifth number maps to -20, and then the next number maps to 30, -30, and so on. Okay. All right, so the next problem is number 5. I think I actually assigned number 5 for the homework. I want you guys to try. I posted a video on a pretty good video, and I think it's made by Ted Ed. So please make sure to watch that. It's kind of fun to watch. That video is actually well made. Yeah, so I want you guys to think about this, and I might want to write up the solution if you guys want. Yeah, but you guys are trying to show a finite group of guests arriving at this fully occupied hotel. How can it be given rooms without kicking out any of the current guests? All right, so number 11 is assigned as a homework problem, but I would like to go over number 10, which is pretty similar to 11. All right, so for 10, we have to give an example of 2 uncountable sets A and B, such that, well, let's first talk about the case. It's such that A minus B is going to be finite. So uncountable. I guess you can have multiple answers for number 10, but I think, what if we give A as a real number, that's uncountable, and B also has to be uncountable. So what if I say B is also a real number, but I can exclude one of the numbers. I can exclude, this means excluding just any number. Let me exclude 0. So what this means, it's all real numbers except 0. Okay. All right, so if I do A minus B, I'll get 0 left out, because this is the whole real numbers, and if we subtract out every real numbers except 0, then we're going to have 0 left. So therefore, this example satisfies and gives it a finite solution. Let's go over B, countably infinite. So we can assign, I'm going to continue to assign A as the real numbers, and B, I can assign this as all real numbers, but I'll use this trick again, excluding natural numbers. Okay, so by doing this, A minus B is now going to be containing all natural numbers, because if you think about it, A is all real numbers, which means every number is in the number line. And from that number line, we're subtracting all the numbers except the natural numbers. So if we subtract out all those real numbers except those natural numbers, then we're going to have the natural numbers left. So natural numbers are countably infinite, so I think this satisfies our argument. Okay. So let's talk about C. We want to give an example of A and B such that A minus B will be uncountable. I can set A to be all real numbers again, and B, we can have B to be all natural numbers. Okay. If we do this, A minus B, then this would be all real numbers minus except all natural numbers. So there we go. This is a uncountable set. So this is a good example to satisfy part C.